and welcome to another video with me. My name is Michael Hansen, as you probably already know, and well, yada yada yada, physics student at University of Copenhagen, so on. Alright, so today I can say right away that this attire is because I'm living on the 4th floor here in Denmark, and it's hot and humid, and so the only thing I can really wear without burning up practically and literally is something like this. So that's how Denmark is. Alright, so I've gotten sort of a challenge, I think it is, by someone on my channel who said try to, he called it debug. I think he actually meant debunk this. It's a video of a man. I'm not sure actually where he lives, because he mentioned two places. He's mentioned Australia and United States. And so what he does is that he goes out in midday, I think it is, and takes a video picture of the moon, then go over to the sun, and in order to show that the moon is there, it's half lit. I think it's called waxing something, I'm not sure. We usually just call it half moon here in Denmark, but I don't think that's really appropriate interpretation or translation. But basically he shows that the moon is there and the sun is there at daylight, which obviously, hopefully, the sun is there when it's daylight. And then he says, well, let's take an example, right? So we say, well, if I can see it here, I think it was in Perth in Australia, then it is practically impossible for someone living on the other side of the earth to see the moon at the same time. And he goes in on a web page which can show you the phase of the moon and when it will rise and when it will go down, and use that for the different places to show that in order from this prediction, actually it is a prediction, right, how the moon, the phase will be and how it look and when it will go up and down, all that. It's predictions from physics. And he says, well, these predictions must be wrong, or that the only way that it can be right is if we live on a flat earth, right, because then both places can see the same moon at the same time. There's a practical problem already there with his assumption, and that is, why does the phase, if the earth is flat and we look at the same moon on a flat plane, right, then why does a person standing here looking up at the moon and a person standing here looking up at the moon, the same moon, right, flat moon or whatever it is, doesn't matter. Why does the phase change from Perth to, I think it was central United States, something like that, right? Why does it change? It shouldn't. So that's the first problem. But I will start by sort of sketching up what his idea was. So basically this is a sketch of his idea. You have him here in Perth looking at the moon, and then you have someone here in the United States trying to look at the moon through the earth. Yeah, that's basically it. And the problem with his approach, first and foremost, is that he goes out in Australia, again I assume it's Australia, he goes out in Australia, takes a picture of the moon, takes a picture of the sun, video but in any way, and then goes in and do a computer simulation, and he infer in that computer simulation that a person in the United States wouldn't be able to see the moon. The problem with his simulation, at least the simulation he shows, is that you see the Earth like this, and then the moon sliding past like this. So you have no real idea what the scale of length is here. And I would argue, because I don't know anybody in Australia and in the United States, I can call and say, hey guys, why don't you try to take a picture of the moon at the same time, and let's see if it's possible. So I don't have that ability. a possibility. It's not possible for me to do that. So what I can do is, from my knowledge of physics and my knowledge of how these systems work, try to figure out a way whether to answer whether he's right or wrong. So my approach will be this. So the basic problem with his model, or the way he present his result, is that he doesn't really say anything about what length scales he's using. So let's make some assumptions. When we're looking at an Earth-Moon system, we can say, well, we know that the radius of Earth is roughly 6,000 kilometers, right? So let's say the diameter of Earth is roughly 12,000 kilometers. Now let's reduce that to be 12 centimeters. So the radius of Earth, the diameter of Earth, let's say diameter Earth is equal to 12 centimeters. The distance, so this is the distance, diameter, distance of Earth. Sorry, diameter of Earth. I'm really messing up here. The distance between the Moon and the Earth, this, let's call it big R, Moon Earth, is roughly 300,000 kilometers. So let's reduce that in the same way. This was 12,000, so that would be 300. Let's just say 300 centimeters. And the distance from Earth Moon to the Sun is much larger, so we can just ignore that. We cannot ignore the if you say that we have at a given point we have angle between the system like this, Moon, Moon, Earth, Sun. This is a triangle. We cannot ignore the angle from a given point and out to where the Earth and the Moon is in relation to the Sun. And we can also not ignore the position of Earth compared with the Sun. But we can say something right away here, right? We can say that, well, 12 centimeters, let's say that's roughly this, right? 300 centimeters, that's bigger than my blackboard. So we have to reduce it any further. So let's reduce it to 1.2 centimeters. And then we have 30 centimeters. Now, then it might be possible for me to put it up here, right? So, but 1.2 centimeters is really small, right? Alright. So I'll try it. Let's just say 2 centimeters, right? So this is, we have the Sun up here somewhere. So I'll place the Earth here, roughly 2 centimeters. And then I'll go 30 centimeters out. And I actually have, let's measure this. Yeah, it actually almost became 4 centimeters, but I don't think it really matters. Let's set it to 30 centimeters. Something like this. So that's roughly here. And I know that the size of the Moon is roughly a little bit less than half of the Earth, so let's just put it like this. Maybe something like this, right? Yeah. Alright. So this is roughly how it would look. Now, I'm just going to erase it again and put it, let's say, around here. And then the Earth-Moon system, I can place the Sun up here. You can see, because I really have two separate variables that I can change here. I have the position of the Moon in relation to the Earth, and I have the position of the Earth and the Moon in relation to the Sun. So this is a practical prop. This can be done, that it looks like this. And now you can always take the very simple and easy example. If I place a person here and a person here, then they certainly both can see the moon, right? But even if I shift them a bit, let's take another color, let's say green. Let's say I shift this person out here and this person out here, then it is also possible for them both to see the moon. And maybe if I shift them back here, it will be problematic, but something like this. So you can change the positions, right? Of where these persons are standing, and remind you that this distance here is the equivalent of 12,000 kilometers. So when I shift these persons just a tiny bit, I'm actually moving them several hundred or several thousand kilometers on the surface of the Earth. So I would say this doesn't in any case prove empirically that two persons on the opposite side of Earth will be able to see the moon at the same time. But as you can as you can also see here, well, actually it won't be like this, but one of the persons will be at daytime, like the man from Perth, and one of them would be at nighttime. So from sort of a mathematical point of view, where you look, you simply observe the system, sun, moon and Earth as a triangular system. Because, as you probably hopefully know, the moon revolves around Earth like this, and Earth revolves around the sun like this. So at a given position of Earth, you can change the position of the moon. I'm not trying to prove that this can happen at a particular date, because then I would have to calculate how the moon and the sun and so on position relative to each other. I'm only trying to prove here or show that it is possible. It is possible to make a configuration of the Earth, Moon, Sun system where two persons of opposite side of the Earth will be able to see it at the same time. Not at the same time when you look at your clock, because there's time difference, but at the same time, like instant, like if I drop something and another person here in Denmark or Germany or United States drops something, we communicate and do it at the same time, right? So that's what I mean. So it is possible. What I don't think is possible, maybe it is actually, but you can see it is also possible to make a system where both persons experience daytime, right? Or let's say one of them is going into the night and the other is going into the morning, right? Daylight, the sun rises and the sun goes down. But it is possible to make a system that would place the sun out here, and then I could place the moon somewhere around here, right? But then they would still be able to see the moon, right? So let's just try it for once. So I place the sun out here instead. Then it would look like this, right? Then I place, let's just get rid of those lines here. Then I place the moon, let's say, somewhere around here. Right? Then the moon would look, let's say, like this. And when it up here is like this, right? So he would almost be able to see the moon, right? We can also shift it a bit down. We can place it like here, then it would be more like this, right? And they would still be able to see the moon at the same time, but they wouldn't be going into to the same daytime, because one of them would be beginning to have nighttime and one of them would be beginning to have morning. But it is possible. Alright, I think that was it, what I wanted to do now. I just wanted to reply on this with a video and not just a comment or a drawing. But if you really want to tackle this problem really seriously, you would have to make a drawing on a piece of paper where you use the correct scaling relations, like scale the size of the Earth and the Moon down, and then put in the correct scaling length from the distances. The distance from the Earth to the Moon, you can just ignore it or set it as infinite, because it doesn't matter, because the distance between the Earth and the Moon is insignificant compared to the distance between the Earth and the Sun. So you can just place the Sun out somewhere and say this is where the light comes from. Yeah. But really, if you want to have empirical evidence from this, you'd have to know two persons, one in, let's just say one in Australia and one in the United States. You can ask to go out and take a picture of the moon at the same time and see if it's possible. I would argue that it is, but maybe that's a challenge for some of you out there. Maybe you know a person on opposite side of the Earth, almost opposite. Opposite doesn't have to be exactly opposite. Alright, thank you for watching.